Hey y'all, welcome back to Alakazam Math Made Easy. In this video, we'll go over the concept of related rates. In the last video, we talked about implicit differentiation, which is a way for us to kind of make more complex systems more approachable. Related rates is very similar because now we're looking at how we can make a conclusion about one quantity given information about a quantity that's associated with it. So what do I mean by that, right? That was kind of vague and a little bit kind of dance around the answer, right? So here's an example. We have a ladder leaning up against the wall. Obviously, it's touching the floor. Initially, we know the ladder is 15 feet long. That'll never change. The ladder will always be 15 feet long. And we know that initially is 10 feet from the wall, where the bottom of it is 10 feet from the wall. What if I was to push the bottom of it towards the wall at 0.25 feet per second, right? How I can determine from that how high or how fast the top of the ladder is rising with respect to the floor, because I'm given obviously the length of the ladder, but I'm also given the rate at which the bottom is moving to the floor. So given the length of the ladder and information about the rate the bottom is moving, I should be able to find the rate that the top is moving. So the good news is there's a pretty solid, generally transmittable set of steps to approach these kinds of problems, because generally we'll be doing the same thing. The first step every single time is draw a diagram. A lot of times professors build this into the exam, so it'll be a multiple part question and part A will be draw the system. Even if they don't, do not ever skip drawing these diagrams because you'll miss important parts of the problem. For example, this was a paragraph long word problem that I turned into a single drawing that I thought was digestible for me, right? So I have all of my given information. I did a model of the system, right? Obviously wall, floor, ladder, easy system to draw, but I have all of the information about the initial points of the ladder, also how the ladder is moving, and I have my unknown drawn and labeled in red so I know what I'm using or what I'm looking for, right? So obviously we're in calculus. We just went over implicit differentiation. We're still in the mood for doing derivatives. So obviously we're going to need to turn this system into an equation. And that equation is always going to be something that relates every single piece of information you're given, right? In this case, we're given the length of the ladder and we're given information about the ladder, the distance between the bottom of the ladder and the wall. So we're given this information and we're asked about this information. So because we're given these three things, you should immediately switch to, all right, that looks like a triangle. And I know something about how I can find, how I can relate all of these things, right? What's that equation called? That's called the Pythagorean theorem, right? Which is x squared plus y squared equals z squared. In this case, I said x squared plus y squared equals L squared because it's the length of the ladder. So now we have our governing equation. We have to, real quick before we plug in numbers, I just want to look at each of these variables, right? So first thing to point out is we were given that all of this is per some unit of time. So we're given position and we're looking at it as it changes with time. So usually when we do equations, it's dy dx, right? How does y change with respect to x? Here, what we're doing is dy dt and dx dt, right? So we're looking at how both of those change with time, right? We're given dx dt and we're asked to solve dy dt, but we're looking at how they change with time. So what does that mean? We know that the x position changes with time because we're given that. This is that 0.25 feet per second. We're also asked for how the y position changes with time. So we know y will also change with time. But L, the length of the ladder, will not change with time. So that's a constant. We can just call that 15. And of course, it'll be 15 squared because it's the length of the ladder squared. So what we're going to do first is we're going to plug in the 15, right? And now we have this equation that's been simplified, right? So what we're going to do then is use implicit differentiation to find a derivative of it. Yes, in this case, you could solve for y, but that'll make you have to do, so let's say we do that, right? So we'll solve for y, that'll equal 15 squared minus x squared all square rooted, right? So that's going to be a chain rule problem, and that's just going to take way more time than we need it to. Whereas if we wanted to just do it this way, we could just hop right across the equation and it'll be easier. So there's that. So now we've done implicit differentiation to get from our original to our derivative. Implicit differentiation. So now let's break down what that equation actually means, right? So this 2x prime term, I know usually with implicit differentiation, we don't include an x prime, but remember, we're not taking all this with respect to x. Usually that was because we took everything with respect to x. Here, we're taking everything with respect to t. So any term that's not t needs to have a prime attached to it, right? Whatever that term is. So that's why we have that x prime attached. So let's break this down. 2 is a constant, that's easy. X is the actual position, right? X is a number that describes the position, not how it's changing. X prime describes how it's changing. The good news is for this term, we're given both of those, right? We're given that initially the ladder is 10 feet from the wall, and that when I'm pushing it, I'm moving it 0.25 feet per second towards the wall. So that's another important thing, is because I've set up this system, I now can call this an XY axis, which means if I'm pushing this way, the rate is actually negative 1.4 or 1/4 feet per second. So that allows me to also set up a coordinate system so that I remember this negative here. So that's that first term. So we have the constant 2, that's easy. We have the initial x position, and we have the rate that we're pushing it, right? The rate that it's changing at. So what happens with this second term? We still have a 2, that's a constant, that doesn't change. Y is the initial height of the ladder, which we weren't given, but we can solve with Pythagorean theorem. So now we have the initial height of the ladder. And y prime is what we're asked for, right? That's how fast that y position is changing in response to me pushing the bottom of it towards the wall. And because 15 squared was a constant, when we took the derivative of that, it went to 0. So now we've broken down our whole equation. We can now plug in the values. Remember, we were given everything except this, or well, we were technically not given this number, but we solved for it. So we now have everything except for y prime, which is beautiful because now we can solve for y prime, right? So here I plugged everything in. And then the step under it, I simplified. And then I canceled these two to get y prime alone after I had added 5 to the other side. And then basically, this could be your final answer, but some professors are really strict about having a radical in the denominator. So technically this would be the answer in that case. Some professors really don't care. Some professors are super strict about it. So if your professor doesn't like a radical in the denominator, change it to this. Radical in denominator. Awesome. And then basically you just do that by multiplying, because this is just a fancy 1, right? This doesn't change the value because it would cancel back down to 1. But by multiplying this radical and this radical, you get rid of it. So that's why we can do that. And then the last thing is to interpret it, right? So it was asking us in the original question way up here, we want to find how fast the top of the ladder is moving 12 seconds after we start pushing it, right? So if we scroll back down to here, we know that the height of the ladder is changing. It's getting higher at square root of 5 over 10 feet per second, right? Because that's constant, right? That there's no way for this number to change. It'll be constant for every time the ladder was being pushed from the bottom at 0.25 feet per second, right? So because that's constant, there's no difference between t equals 1 and t equals 12. Sometimes what you'll do is you'll have y prime equals like 5t plus 2 over 10. And in that case, you would plug in t equals 12. So you would have 62 over 10 is 6.2. That in that case, if anytime you get the derivative with this t in it, that would allow you to plug in the value that they're asking you to consider it at. And then from there, you could move forward. That would be your answer. But here, like I said, because it was moving constantly, it doesn't matter what time we're looking at, the constant will still be the same. That's the nature of a constant. So if you learned something from this video, please give it a like. This was, again, related rates, how we can find information about one value given how a value that's related to it in some way is changing, right? So if you have questions about this concept still, go ahead and leave them in the comments. I'll answer them as soon as I can. Otherwise, if you want to stay up to date when I add new videos to the channel, subscribe and turn on your notifications. That way you get notified when a new video is added. But other than that, as usual, best of luck.